So today, just a minute. तो वहाँ पे hello. Hello. Today.
Yeah, that's good.
Okay.
Hello?
Yes, ma'am, give us just 1 minute.
Hello.
Yes.
Am I audible? Oh, okay.
Yes.
So, hello everyone. Today, Aanchal, Rahul, and me are going to present a paper on unsupervised monocular depth estimation with left-right consistency. We want to build a system that given an input image like this and the output image will be a dense map like this. In this case, brighter means closer. So why are we interested in depth? Depth is crucial when it comes to understanding the world around us, such as navigation and mapping. So if you are a robot, you would like to know where you are, where you want to go, how far away things from you. If you want to grasp things or interpret, interact with our physical world around us, depth is crucial. So how do we usually get depth? The reason we can perceive depth is with our beautiful eyes. If you notice, when we look close objects with one eye, we will see a difference between both perspective. But when you look something far away, like mountains or buildings kilometers away, you won't see a difference. This difference are automatically processed in our brain, and we can perceive depth. Animals that have eyes aligned far right or far left, they cannot perceive depth because they don't have any common perspective. Instead, they have a wide angle perspective. Now, let's focus on a system like our eyes. If two cameras are aligned vertically, the observed object will be in the same coordinates vertically. Difference in the x-axis, like there will be we can only focus on x coordinates to calculate the depth, since close object that will have a higher difference in the x-axis. But to achieve that, we need to calibrate cameras to fix lens distortion. After the calibration, we need to rectify the system. If we calibrate and rectify our stereo cameras well, two objects will be on the same y-axis, and observed part will be found in the same row of the image. From there, it's the only difference between the pixels and the depth calculation. So Rahul has a right back, so he will explain this further.
Hello everyone. So I will explain how using a binocular system you can estimate depth of an object. One. So suppose these are your cameras. Distance between them is say B. So this is your image plane, and you have an object here. So your images will be somewhere here. Uh, so these are both are calibrated and this they have fixed focal length. Yes, and yeah. So we want to estimate this z, which is the distance between the object and the camera. So let's draw perpendicular lines from here. So I'm calling this x1 and this x2. So so these triangles, this triangle and this triangle are similar, right? So so we have this relation x1 by call this b1. So this entire distance is b, and calling this part b1 and calling this b2. b1 plus b2 is b, the distance between the cameras. So now, so you have this x1 by b1 is equal to f by z. Similarly, you can get x2 by b2 is again f by z. So if you calculate, if you add them, so x1 is b1 f by z and x2 is b2 f by z. So x1 plus x2 would become b1 plus b2 times f by z. So so this becomes your d. So d is bf by z. So you can see that if your cameras are calibrated, the sorry, so we want to find z. So we'll just reverse these. So my distance is this. So bf by, so b and f are fixed because our cameras are calibrated, and so b and f both are fixed. And so if we can find this d, so that is the disparity, then we can find the distance uh, of an object from your cameras or observation point. So yeah. So you can do this similar argument if an object is outside this, like if an object is here, then you can similarly you can construct like this and you can get a similar result, but instead of x1 plus x2 you get x1 minus x2. So this way it's the same process. So I'll show an example of how you can find yeah. So you have this relation d by b is equal to f by z, or z is fb by d. So in this image you can see that, so we concluded that d and z are inversely proportional. So you can see from the image that the objects that are close, like this lady, so you can see that, so closer image have la- larger disparity as compared to objects that are further. So if you get a left and right image and if you combine them like this, and if you have a mapping like you take uh, like this eye and this eye, suppose you have a correspondence, then you can find the distance between these correspondences, and then you have the disparities, and using that formula you can find the relative depth.
So this is an explanation for what Monalisa said earlier, right?
Yeah.
Yes.
Okay, so yeah,
So,
Monalisa will continue with the. Right.
so why are we interested in monocular depth estimation? Let's say we want to get depth from an old photograph like this, but this is not possible as we do not have any depth sensor at that time, or the photograph that doesn't this like photograph, it doesn't contain any depth information. So also we can have a physically restrictive setup such an endoscopy. In this case, we don't have any we don't have space to put a stereographic camera or a laser at the end of the endoscope, but we want to collect the estimation. Because of these limitations of binocular method, monocular depth estimation is very useful. So, depth estimation has a long history in computer vision. However, most of these techniques rely on the assumptions that multiple observation of the same scene of interest are available. This can come in the form of multiple viewpoints or observation of the scene does not the observation of the scene under different lighting conditions. To overcome this limitation, recently many researchers are working on monocular depth estimations as a supervised learning problem. These methods attempts directly to predict the depth of each pixel as an image using models that have been trained offline on large collection of ground truth depth data. But these methods needs large image collection and their corresponding pixel depths, which is a challenging problem. So in this paper, they have replaced the use of explicit depth data during the training with easier to obtain binocular stereo footage. They have proposed a novel training objective that enables our convolutional neural network to learn to perform single image depth estimation despite the absence of ground truth depth data. So from here, over to you.
Yeah. So as Mona Lisa mentioned earlier, so if you are doing a supervised learning task, then you need input images as well as the ground truth depth data. So for that, so there is a kitty data set that has this corresponding images and there's depth maps. But as so this is the car that was used for data collection, and as you can see, so you need two cameras and also a laser scanner uh, that actually calculate the distance between different objects. So calculating, like, getting thousands of images for your supervised model would be very expensive and tedious task. This way. So instead, we are using unsupervised method. So for training, we have left and right images of taken from a stereo pair of cameras. So, but now instead of using these two images for test, like during test, we do not need left and right. So we are training our model with left and right images, but our final aim is to learn the depth map just using one image. So for that, we will learn. So given a left image, we'll try to learn the right image. And once we know the left and right images, we can compute the disparity and hence the depth map. The last point I will explain later. Uh, yeah, so data augmentation, we take the images and we to create more images, and we flip the images horizontally on vertically, and then also swapping their depth maps, because if you flip an image, then the right and left corresponding depth maps will also be reversed. Yeah. So I'd like to explain something before showing this slide. Even though our task is to like, get, so once you have a left image, your task is to get the corresponding right image. So one way that you, so there is one baseline model that just uses uh, left images and tries to estimate the right image, and just you take the L1 norm of these two estimated images, and you learn it that way. But we propose something else. So given an image, you you estimate this. Yeah, so there is one intermediate step that we want. So we are actually calculating this right disparity using left image. So where this IR would be just IL plus this. So yeah, as we saw in the previous few images back, that a right image is just like different objects are shifted by some amount. So you can construct a matrix that gives you shift for each pixel. Okay, so we are learning that. So using these two, we will have constructed this IR. Okay. But then we have IR. So this is the original image. So what you want to do is you compare these. You want to minimize this, but uh, you also want to estimate this. So taking input as your estimated map, you want to calculate the left disparity, and you want to also reconstruct the left image, and also you try to minimize this loss, this difference, as well as this difference. So this turned out to be to perform better than the baseline model, where you're just estimating this and you are minimizing this difference between the estimated and actual. So for this, you need a function that, given a right image, it also gives you a left disparity and the left image. So while training, we are trying to learn this map, but along with that, we are also while training, we are also trying to learn this map, and basically we want this map to be both these maps to be invertible, so that our right and left images are consistent, and this map is invertible, and both of them, we need them to be inverses of each other. of consistency, and this uh, increase the performance of the model.
And so the difference between IL and IL tilde, you will sort of take it as the reconstruction error, right?
Yeah, so we will include that in the loss.
Minimize that one.
Yes.
Okay.
Yeah. So we have 6 different terms here. Now, I'll explain what these each of terms are. So AP, ADS, and ALR are just parameters that we choose. So the first one is appearance matching loss. It's AP. So you're calculating it for left as well as right. So So this is some similarity index that they have used, and there's a complete paper on this. So just assume that this is some similarity, takes two images and calculate the similarity. So what you have is, so using left, you are calculating the uh, right image, and using the inverse function, you are reconstructing the left image. So this term gives you the error, reconstruction error for the using this similarity measure, and 1 minus this gives you similarity, and 1 minus this gives you the kind of distance. So we are using a combination of this L1 norm as well as this measure to get our reconstruction error. So this is reconstruction error for left image, and same thing we do for right image. So there are two terms for left and right. Then there is disparity smoothness loss. So here what we are trying to do is, given an image, so you have an image and your background. So so the disparities are discontinuous. Yes. So we don't want that. We need a smooth transition from here to here. So, so this they haven't mentioned much, but what I could get was, like, given a IL, you're getting a DR, and you're getting a estimate of the right image. So you want these derivatives to be, so this is contributing to your loss. So kind of you want these derivatives to be small, and these derivatives to be a little larger. Yeah. So the third term is right left disparity consistency loss. So as I showed the diagram earlier, so we are calculating the disparities from left to right as well as from right to left. And so so as we saw in these images, so these left disparities and right disparities, they have to be equal for. So, this gives you the difference between the estimated right disparity and right disparity using left image, and left disparity using right image. and we are minimizing that. So the more functions you have in the loss function, you get a better result. Yeah, sorry, I forgot to mention that this the model that we are using is so this left image it goes inside a CNN and it gives you a disparity map, right? And similarly, you're doing that for right. For consistency, we are computing disparity maps for horizontally flipped image. So uh, given an image, if you flip it, the distance should not change. So for consistency, we are calculating for both of them. And then yeah. Also there is one problem that that you have with this arrangement. So you're looking at this.
Hello, Rahul. Would you please
Yes.
let one of your other team members proceed if you're not feeling good?
So now just last slide and then Aanchal will proceed from here and she will also show you the run the code and show you.
Okay.
Yeah, so given some scene, uh, you are calculating. So this is suppose some object and I think this should be vertical flip. So yeah, so left and right image, like they will have this. So there will be an inconsistency. So we are filling that by flipping the image. Like so, 5% of the uh, pixels on the depth map we are filling by horizontal original image and the flipped image, and then the middle we are like getting the average. So you first take the image, you find the disparity, you flip the image, get the disparity, and again flip that disparity, and the middle part would be the average of both of them. So Aanchal will explain from
Sorry,
here.
but it's not. So, Aanchal, will you explain what he meant by flip the disparity? So, what the previous thing I didn't understand actually.
Yeah, so if you're flipping the image, the depth map will also be flipped, right? And if
Yes.
the middle part you want to fill by the average, and if the depth map are flipped, then you won't get anything in the average. So you need to flip the depth map. So it aligns with the original depth map. That is what I mean.
So by flipping, you mean reflecting in the
Yes, yes,
reflecting in the horizontal axis or vertical axis, something.
yes. Vertical. Horizontal,
So you're
but vertical.
reflecting in the vertical axis, and then
Yes.
you're saying that the disparity that's there on the right side will appear on the left side also. Suppose you reflect from right to left,
Yes.
and then but what do you mean by? Okay, so the disparities basically will be seen on both sides. The same disparity will be seen on both sides.
Yes.
And then the central part of the final disparity map means?
Like you will have two disparity images, but uh, but when you are taking a picture from left and right, so there is some inconsistency in this part. So the model will try to, like, if you want to convert a left right view, then it will.
Oh, now this, I see,
Yeah.
I see. So there is a disparity on the left, there's a disparity on the right. Now you
Yeah.
reflect this entire image through a vertical axis
Yes.
and look at the corresponding disparities. Now you take the average of those two. Is that what you're
Yes.
saying?
Yes.
Okay, okay, got it. Yeah, okay. Please go ahead.
Yeah. I'll stop share.
So now let's look at the data set. The data set that is used, the paper has mentioned usage of two data sets, namely Kitty data set and Cityscapes data set. We have focused on Kitty data set. So this data set contains 42,382 rectified stereo pairs from 61 scenes. That is two images for each scene from left and right view. So each image size is 1242 cross 375. So this is what the training images look like. And this is how the test images look like. The code is implemented, the code for training and testing is implemented in TensorFlow version 1. There are 31 million trainable parameters, and they use title X GPU on dataset of 30,000 images, and it took 25 hours to train. Now let us look at the code. So this is the code to train the dataset. This function evaluates the error metrics for the dataset. Then we have function to calculate the average gradients. This is the main part. This class loads the data and stores it as tensor. This is the main part where we define. This is the class for monodepth model where we define the architecture of our CNN. Then this is the actual function where we pass the parameters and train the data set. These are the parameters. So due to hardware limitations, we couldn't train the data set on the whole, train the model on the whole data set. So for creating depth maps, we took the pre-trained model that was provided with the paper. So that pre-trained model is stored as model kitty.omnx. This is how the image depth maps look for some of the images. Here we can see that the nearer regions are more bright than the farther regions. We also created depth maps of some of our own images and some images we took from the internet. These are some of the error metrics that were uh, 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 here. The paper has compared the error metrics with some other implementation. So let's look at the limitations. So one of the limitations is occlusion. So if we take the image from two scenes, like the first one is left scene and the second one in this case is right. So this object is hiding in the first image. This object is hiding, overlapping with the object in the back. So here in the depth map, it seems like it's the same object. Also, our method requires temporally aligned stereo pairs. Yes, ma'am.
So you have this in the second image, it looks better, right? That's because
That's a
the
different
camera has
set
moved
Yeah,
of-
that's
towards
separate.
the object.
Yeah, so they're actually distant images, but because of the angle that we are taking the picture, they in the depth map it looks like they're in the almost same distance.
Yes, ma'am.
Okay. No, I didn't realize earlier that the camera is moving. Okay, got it.
Yes, ma'am, because the images are taken from that card. So our method requires temporally aligned stereo pairs during training. So it's not possible currently with this model to train from single view dataset. But after the model is trained, then we can use a single view image to produce depth maps and then calculate the depth. Also, if there are some transparent or some shiny regions in our image, then it produces inconsistent depth maps. For example, here we can see that this glass window is transparent, but our depth map has shown this region as darker, even though this region is mirrored. So hence we come to the end of our presentation. Thank you. Also, ma'am, I forgot to add that we also tried a code on some older images, and here also it was not producing the correct depth maps.
I see. Can you scroll through your results a bit slower?
Yes, ma'am.
Earlier. Now that was an old image, but yeah, so I think it is about whether the objects are clear or sort of
Yes,
the
ma'am.
background in the image. Yeah, so here I mean it's pretty good, right?
Also, sometimes when the images were very farther, then also it produced inconsistent depth maps.
This we have no idea why it's not detecting the wing because of the glass.
I mean,
Probably,
what
I'm
do
not
you
sure.
expect from this depth map? Just the depth of the points.
So this is relatively very close.
Tiny, yeah, that is very close, but that is very small also as compared to the other part of that image. Yeah, I guess because as she mentioned, if there is glass or there are shiny objects, then that's not working so well.
Yes, ma'am, that may be the reason.
Probably has to do with the glass. Also not so good, right? Because
farther images, yes, they are not properly.
yeah, this is also not. But probably this is taken in the night also.
Yeah, but the closer images are coming good, like the trees, the gate, and the board. But the CMI it's showing that CMI is farther than the sky. That is some inconsistent result.
Yeah, exactly. I guess because this lighting condition seems to play some role here.
Yes. basically it's inconsistent for further objects. So can you go to the last image?
This one.
Even here, the buildings that are very far are not, they are visible, but yeah, even more further images, that's a little inconsistent.
So I missed out what was sort of the accuracy of that model.
Mm. This is what
Yeah, can you?
was implemented.
No, can you just describe? So these seem to be some older papers on the top. The
Yeah,
trains.
the top, there are some older papers, and in the paper we have compared the results with older papers. Model.
So I don't know what this means. What is no LR, then hours, people?
Now,
I mean,
so PB means post-processing. So this model is without post-processing, and it's not supervised, and the data set is only a kitty data set. These models are trained on Cityscape plus a kitty data set. This one uses ResNet architecture.
So the no LR is the baseline model that we just produce the right image and get the loss using that with and I mean
so
in
delta
our
is
method
enough.
we are
There is no left. I mean, there are no left and right consistency.
What
in
is
our model
delta?
we are sorry.
Sorry, what is delta? Hello?
Yes, ma'am.
I think that is some parameter used in training.
We calculated average gradient.
Well, okay. I don't have any other questions. Does anyone else have questions? Okay, it seems like no. All right, so with that, we come to the end of our series of presentations. All the presentations will be uploaded to the CV 2022 playlist, and you can take a look at them. Some of you might have missed some of the talks, but most of the talks were very useful in terms of understanding various parts of deep learning. Also, we saw a gamut of areas covered in these presentations. So I thought in general the presentations were nice, and also I hope that they contributed to your learning of computer vision, which was the aim of having these presentations in the first place. Okay, so with that, I would like to take leave. So there is just one point that, so this is apart from different